make a little recording of this so I can put it online afterwards. Alright, so I'll just start with a little bit of information. It's okay if you want to ask questions on the way, that's why I do this here instead of putting out a video. So you can push this raise your hand button down to the bottom right there if you would like to say something, or you can simply just feel free to put on your microphone and ask directly. Or you could write something in the chat, but I think it's, yeah, and I'll try to answer the questions as we go along, just like we do in a normal section. Okay, just some general information first. Exam dates, based on the doodle poll, those who answered it, ended up being set from the 18th to the 21st of May. So it seemed like most people who voted were okay with that. If you're not, then please let me know by mail. And we will try to set up an oral exam the week after, and it seems like we have to do most things through this Collaborate Ultra engine for the rest of the course, because my guess is that this will continue at least to the end of May. But all assignments, all labs, all additional lectures and those sort of things we can do through here. So my guess is that this course can basically run as usual. I don't think it will be any obstacle for us to finish up. Okay, another thing is that once this lecture is over, Shadows is the last obligatory lecture, it's possibilities to take up topics that you think should be covered more in depth. Because we thought we would invite teachers to talk about sort of like outside things, but that's going to get a bit more difficult now. So next week I think Carl will talk a little bit about CMake, but after Easter's we also have some slots for lectures where you can talk about things you need. So I will make a page on Wiki. Yeah, live coding, okay, I'll write it down. Any other suggestions? I can also write it down now if you have something that you would like us to talk about. Any other? All right, if you come up with something, you could tell me later, or you can send a mail. And I'll also make a page on GitLab Wiki where you have the possibility to fill in subjects just as you filled in these tables with group assignments, right? So, and then we can look at these options and figure out which one to go through depending on what people want. So I may set up a poll on that later. Right, and then it's the grading of assignment 1. It got a bit delayed, unfortunately, because of this corona situation, but we're working on it now, so hopefully during next week they should be ready, and if not, I will try to put them out during Easter, so that when Easter is done you should have the results on that one. So are there any questions? Feel free to turn on your microphone and speak if it's something you wonder about at this point, or during the lecture. Okay, so then I will just go on with the lecture. Okay, so the last topic is shadows. Within this there is also a little bit about bump mappings and normal mappings, which is also listed in the course curriculum. This talk would actually have fitted best right after the lighting and colors lecture, but since it's not obligatory for you to use it on your assignment, and that is a bit more difficult, we chose to postpone it to after we talked about object loading, which you have to use, and scene graphs, which is also something you may use if you'd like to. But of course we would be more than happy if you'd like to use this, and we would also be impressed if you're able to make this in your assignment. Carl and Leon on their assignment last year used shadows. So if you look at that demonstration of Carl on the channel, on this course's YouTube channel, you will see an example of using shadows. And what they were using is called a shadow map, which is one of the topics I will talk or use most time on today. Okay, so I said before that lighting and color is really important for how an object appears, and also getting the perception of depth and 3D for your eyes, which is basically a flat space. Shadows is a very, very important ingredient in that, because the way shadows are cast really gives you a impression of orientation and depth in general. And you can also use shadows to make height maps and depth profiles, basically. So it's a very important topic, but it's a bit more difficult to deal with. So this is sort of like taking you now a bit further beyond where we've been dealing with up until now. So you're getting, you know, towards another level with this thing. Okay, so yeah, this came up straight away. So I tended to ask the question what a shadow is, but it's basically listed here, so I can just read out. So basically this is taken from definitions in dictionaries. So it's a volume of space that receives no light, or light that has been attenuated through obscuration, redirection, or transmission. Or a shadow is a dark shape on a surface that is made when something stands in between a light and the surface. This something is usually referred to in this course or in graphics as a occluder. Right, so why are they important? Well, this image really shows that there's a lot of information contained just in the shadows. So just by looking at the shadows cast from in this image, without the actual objects actually being in the image, you can tell a lot. Like you can say how many people there are, you can say that some are males, some are females, some are wearing pants, some are wearing skirts. You can see where the light is coming from, that it's most likely a directional light source, those sort of things. So lots of information contained in the shadows. Also, you can of course tell whether or not a object is transparent or opaque, depending on what shadow it casts. So for example, you will see that this object number C here is definitely opaque because it casts a completely dark shadow, whereas A here is transparent. And transparent object, you can also of course say something about the chemical composition, because you will see what parts of the electromagnetic spectrum is absorbed and transmitted through, and that basically tells you something about chemicals. So there's rich information in the shadows, to say it like that. So before I go on, I will just show some mind twisters, because you can also use shadows to fool your perception, which really also shows the importance of getting shadows right, unless your intention is to fool someone's perception, that is. So if you take a look at this picture, it's basically, I guess it's a picture from the moon, probably. It's showing an impact crater, and I think most people see this as being a crater, not a hill. And this has to do about the fact that we assume that light is coming from above, and in this case you would assume that it's coming from the upper right corner here, and then a shadow will be cast in this part of the crater, and it will be lit up on this side. So that's what your brain assumes. Now if you do like this, oops, then is it a crater or a hill? Yes, that's what it looks like, but actually it's the exact same. It looks like a hill, but it's the exact same picture, just rotated 180 degrees. So if we take this crater and we turn the image upside down, then suddenly our brains tells us that this is actually a hill. And that is because of our assumption of light coming from above, right? brain assumes this, and therefore we will assume that this side here, which is lit, has to be standing out of the ground, and this part behind here, which is dark, would be on the other side of the object. But with a little bit of reasoning, we can see that it's actually the same picture, just rotated 180 degrees. Then we have another one. It's exactly the same. If you rotate this one 180 degrees, then these two columns will change roles, basically, because here you assume that this one is actually standing up, and here you'll assume that this is a pit, right? And again, that is because light is coming from above and then lighting up this area and casting a shadow here. So it goes to show how important it is to have shadows in the right way. Now here's another problem. Can anybody say which is the front face of this one? Is it the face over here, or is it the face over here? Well, the fact is, it's impossible to decide. It's impossible to decide because point one, you don't have any perspective here, so there is no both of these faces are of the same size, and there is no shadow casting, meaning that it's up for grabs what is front and back of this object. Whether it's this face or this face over here. And you can go on and make many of these mind twisters by shading in different, or using different shades of gray on on different parts of the object. So depending on which cube you look at, it's really hard to tell which of these cubes are in front or not. Now, of course, these cubes are made particularly to fool your perception. So both of these objects are called bistable because it's really no way of determining what is what here. It can be both. And here's another example. Given the shadows that some object casts on a background, can tell you something about how far away it is from it. So in a sense you can say that these are different sized objects that cast different shadows, and you would assume that the one to the right here would be further away from the background than, for example, the one to the left, just because of the way it casts the shadow here. But it could also be a picture that fools you by saying that all of these are the same size, and you just manipulate the shadow here, and then you get the impression that this is actually higher up above the plane than the others. And here's a neat one. Can you tell me which one is the darkest of square A and square B here? Anyone? Yeah, so that's what. Yeah, so that's what I think everybody would say, and that is because you make an assumption that this occluding object here is casting a shadow onto this board. But this is actually a trick, because your perception will also. We have something called color consistency. That means that whether things are in shadow or outside the shadow, you would see sort of the same difference in color, or be able to differentiate colors. But if you draw a similar colored line as this square over to A here, you will see actually what's the truth. And this is a bit of a surprise actually, because it basically tells you that A and B are the same, have the same color basically. So try to think a little bit about that and figure out what mechanisms are lying behind this and why this actually happens. But again, it comes back to how shadows are used and how they mess with your brain basically. All right. Yeah, last one. If you didn't have a brain to make sense of the world, you might as well say that this woman is actually standing on a flying carpet, right? But of course your reason tells you that this is probably the shadow of a flagpole with a flag on it. But without any other assumptions, you know, this may even look like she's floating in thin air. So again, it goes to show something about how shadows work. Right, so let's get down to earth a bit and start to talk about you know, how to deal with this. So first and foremost, yeah, I basically said that shadows is basically where you don't have as much light as in other places. But as we've seen, you can basically estimate depth and height from how shadows are cast. You can also do something called shape from shading, which is a bit interesting. You can make 3D models out of single images just by looking at how shades are cast and how light is reflected off the surface. So I'll show one example of that a bit later. And you have two broad categories of shadows. One is from object to object, which is shown here, for example, by this armchair that is casting a shadow on the wall. And this can be faked, so you can impose these shadows into your rendering, and you may you know, think that there is some object there that is actually not being there at all. And they're quite easy to deal with compared to these self-shadowings. For example, this armchair will also cast a shadow onto itself, which will make it occlude itself in a sense. These are more difficult to deal with. Any questions up until now? Okay. So, a month or so ago we talked about textures. Mainly we talked about texture as being some image that you upload and put on top of your primitive, whatever that is. For example, a quad, or you know, in more general cases it would be a geometrical object. Now, there are other textures I didn't talk about because we weren't really ready to talk about them, but there are some interesting textures there you could use to have a low-cost way of making an object look rough, for example, or make surfaces look rougher than what they actually are. So, something called a bump mapping is basically shown in the middle here. It's a texture containing of lighter and darker regions. This particular one, for example, could be generated by a random number generator, picking numbers between 0 and 1, where 0 is black and 1 is white. And then I added this little spot here. So if you take a sphere with a certain lighting on it, and you coat this object with this texture, then when you shine light on it again, it will actually look like an orange. And that's because all of these darker regions will attenuate the light and make this impression of shadows that makes the object looks much rougher. So this is very often used because it's a much more low-cost way to make objects look rough than just doing this triangle by triangle, which would be a very complex task. We have also something called a normal mapping. Now here the texture itself is just a normal vector field. So I show in this example here you have a line, or this could be a plane in general. Now on a plane the normals would usually be standing at right angles, like the one in the middle here, right? But you could coat this plane with other normals. So you could take a normal field from another image and impose it on this plane. And then these normals would not be standing at right angles with this flat surface anymore. So when you shine light on these normals, you remember that light coming in will always be symmetric around the normal vector, so it will bounce off in a symmetric way, or a reflected way around the normal. So if you're normally standing like that, when you compute your lighting, when the light comes in here, it will not bounce off in this direction, but it will bounce off in a very different direction, which from your impression of this object, this flat surface would actually look like it's curved or ragged in some way. So you can basically change the way that light bounces off a surface by coating it with this normal mapping as a texture. So I like this example down here. You have this staircase that you would like to look very rough, Patching this together triangle by triangle would be quite daunting, so you make a smoother model and then you coat it with some normal field. And then you can, for example, see in this area here, you don't really have any marked shadows, but when you put these normal vectors on, you suddenly get these shadows that makes the object appear like it's much more rough than it actually is. So these are just techniques where you can use to manipulate how light is cast off and how shadows will be made in order to make your object look a bit more realistic. And it's low cost, so that's an important thing. Okay, the last thing is actually the fact that you can make 3D reconstructions from only one image, and that is called shape from shading. So you basically use these lighter and darker regions to tell you how deep the object goes, in this case in the C direction, and then you can basically make these 3D models. Here are artificial images, but in this case you have a more complex image. This is an image taken from a pill cam that is traveling through someone's digestive system. And you can use the shading information in this image to make this 3D profile, which you can rotate around. And this is very useful for doctors, for example, because they have the possibility to see much more features here that they would not be able to see as easily in the flat image. So there's some neat things you can do with this. Alright, so let's get down to business and talk about how we compute this and how we render shadows. Are there any questions before I start with this? Okay, so I'll just go along. Now, rendering shadows is not simple. You always have to render at least twice or several times in order to make the shadows appear in the right way. And the more realistic a shadow is, which we show along the axis to the left here, the more difficult it is to render, and the more times you have to render your scene to make it appear in this way. Of course, there are ways of making things looking more realistic by doing fake things, but to really make it realistic, it's computationally difficult. So, in the real world, for example, when you're inside a room and you have this area light up here, you will have light rays going towards some blocking object, which is called an occluder. It's this green line here. And these direct light rays will of course not reach the surface underneath. But of course this light will travel, bounce off walls in the room, and then some light will be reflected back to this area nonetheless, meaning that this area is not completely in darkness. On the other side, you have something that is computationally simpler, but even in this case you have to render twice in order to be able to make the shadow. So the simplest case, in which I will illustrate afterwards, is basically you have directional light, you have one occluder, and you have a hard shadow cast onto the object below. And then of course you have these things in between, which is point light, for example, where light is traveling in a cone. This you can deal with something called a shadow map, a shadow volume, which I will deal with towards the end of this talk. And then you have this thing in between, where you have an area light, an occluder, and you have this gradual takeoff from completely shaded to completely white. And that has to do about the fact that the light source has a spatial extent. So you will have the shortest path from the light source that will cast a hard shadow, and then you will have a more remote part of the light source that will cast a much weaker attenuated point over here. So it makes you go from let's say black to white in a more gradual way. So these are roughly the types of lighting and the complexity involved in modeling them. So the rest of the talk I will mainly deal with these two here, and I'll start off with the most simple one. So how do you go about to implement this? Now I just showed a very simplified lighting model, the Phong model basically, which we remember has ambient, diffuse and specular components. And this is more or less the same as before, except that now I added this shadow term here. And basically this is a fraction of a light that is received at any surface where a shadow is cast. So it may, in the most extreme case, for example, be 0, then you will have a completely black area. Or to make it look a bit more realistic, one may have some value larger than 0, but still small. That will make it look like there's some other light being able to travel under there, so you're closer to this indirect light situation over here. Okay. Now, anybody has an idea why we don't have this shadow term in front of the ambient light? Well, as I mentioned several times before, it's the diffuse and the specular components that are directional light sources. Ambient doesn't have any direction. That means that it doesn't really either cast any shadow. It's basically the same overall. So the shadows are basically connected to diffuse and specular lighting that has a incoming direction. And of course, if you have a point light, you set this to some number close to 0. If it's an area light, like the one showed over here, then this value can take something between 0 and 1, because you will have a gradual takeoff depending on position. So, of course, this looks very easy because you have the Fung model and then you just scale by some shadow term, but of course the big problem is to determine what this shadow term is in a general geometry when you render this onto a screen. And that's really where the difficulty lies, is figuring that out. Because this will change through space in 3 dimensions. Okay, so just mention some of the influence factors we have to take into account. We already seen that we have to look at the light sources, so directional point light or area light will cast different shadows. Direct versus indirect we also saw, but also the material matters. It matters if the material is transparent, if you have translucency, or refraction that sort of bends the light through the object. All of these things will make it much more difficult to deal with shadows, and therefore this is more like an advanced topic that we will not deal so much with today. I may talk a little bit about it towards the end, but it's too complicated for us to deal with at the moment. And of course the geometry matters. If you have a simple polygon, like a quad for example, then it's rather simple to compute a shadow. Of course, if you have more complex objects, this becomes more difficult. Now, the shadow map I will talk about can actually deal with quite complex objects, and that's why it's I will emphasize on it, because it's quite neat given the fact that it's still rather simple to compute. Now, one thing is that typically all real-time algorithms for casting shadows have some common limitations. They usually don't deal with transparency, so this situation is not dealt with in that case. You may have several offline sort of rendering algorithms that I talked about for, like path tracing and photon maps and ray tracing and those sort of things that can help you deal with that situation, but they're not really real-time rendering methods. And yeah, they have a hard time dealing with indirect light, as I just talked about. Atmospheric effects like fog and scattering through water droplets is also very difficult to deal with, so it's typically not dealt with in these simpler algorithms. And wave properties, like the thing you see on the image delta over here, is also very difficult to deal with. So, but given that we take all of these things out of the equation, we still have to, the big challenge is to figuring out whether an object is in a shadow or not, and then of course finding the fraction of light that is received from a particular light source at any given point in the scene. And that's what I will deal with for the rest of this talk, basically. Okay, so compared to lighting models where you have some rather few ones that is used again and again, in shadow algorithms there's really no particular one that is known to be best. It really depends on context and what you want to do, and it's really highly research based, so there's a lot of research going on in this area. So that opens the possibility to make you know, research projects or master or bachelor tasks that people can solve, because it's really a lot of different models working for different different purposes. Oh, let me see. Okay, so they're just listed here. I will talk about a few of them today. I will start with this planar projection because it's very simple, but it's not very useful, so I'll not spend so much time on it, but just to show the concept. Then I will move on to shadow maps, which is really the one we will use in this course. If you're going to use this, it's probably going to be this one, because it can deal with more general situations, and it's also computationally simple enough for us to be able to implement it at this point. I think that next week we may put out some labs that is voluntary for you to work on. One will be about implementing this shadow map. But it will of course also be possible for you to ask questions about it if you need. We also have these shadow volumes, which I will talk about towards the end today. Okay, so let's just start with this planar projection. So basically it's quite simple. Sorry? Okay, so it seemed like someone was turning their microphone. No one? Okay. Anyway, it's a quite simple approach, but it's not very flexible. It can only deal with plane geometry, like flat surfaces and very simple objects. So how it works is that you have your light source over here, and then you render your scene once in full lighting, and then you're basically drawing lines from this light source to every vertex until they meet in this case this flat surface underneath, and then you make a vertex at this point. And then you do that for all the vertices in the object, and you will see that you get this polygon down here, which represents your shadow volume. And then you render this scene again, and you color this new polygon in a darker color to make it appear like you cast shadows. Now, if I had a blackboard, I could basically go through, because it's quite simple linear algebra to show how to compute these vertices. It's basically using inner products and ratios of them. But since we're not going to use this in this course, I will not spend time on doing that. And if you're interested, you can go to this YouTube video here, which I show step by step how you can compute these different vertices for this particular case. And this video also has a part on shadow volumes if you would like some explanation about that. So it's going quite nice and slowly through these things. But the main limitation here is that it only works with planes and plane geometry, and therefore it's not really interesting, because we will deal with much more complex scenes. So if there's no particular questions about this method, I will just skip to more advanced things. Alright. Now, to deal with more advanced shadows, we have to talk about something you haven't dealt much with in this course. Some of you may have dealt with frame buffers if you try to do efficient drawing, for example, because doing efficient drawing, really the key is to deal with these frame buffer operations. But mainly in the lectures we've basically been saying that, well, this is the last stage of the OpenGL pipeline. It happens after the fragment shader, and really haven't touched much upon it. But to deal with shadows, we really have to talk about it. So I'll just go briefly through these operations that is available for you there. So you have several tester operations, and usually these are disabled by default. So every time you want to do any of these tests, you have to enable them. And that is because all of these require extra computations or operations to be performed before you place your rendering to the screen. So the ones I will talk about today mostly stencil tests and depth tests. They are needed to cast shadows. You also have something called a scissor test, which comes in front of all of them, and basically that is to clip out a part of your scene that you will render. So it's either what is in your view, or if you would like to cut out just a smaller window of you, you can use this scissor buffer or scissor test to basically cut out a part of your scene. And then you have this blending operation that some of you probably have been dealing with when you made sprites, because it's a way of blending an object better towards the background. So I will not talk about that either today, but you usually use this also when you impose and shadow into your scene. So you have your scene fully lit, and then you impose the shadow on top, and then you blend them to make it look nicer, basically. But I will focus on the stencil and depth tests. Now the stencil test is a bit, a bit weakly defined. It's basically a general purpose buffer where you can do a lot of things. But mainly you have the possibility to set bit masks where you basically put up a test to say whether or not you change the bits or the numbers in this mask. And the bits you change are in the stencil buffer, which is basically a buffer that stores a single number or a single bit per pixel, depending on what you want to do. So it doesn't have any particular meaning, so you can do a lot of things with it. But as the name says, it's really connected to being a stencil. So I just show a picture of that, which is over here. This is an example of a stencil, and this is exactly what it's about. So for example, in your buffer, you could put up ones where you have the white regions here, and you can put zeros where you have the black regions, and then you could ask OpenGL to only color the regions that are black here, for example. So this will be the same as putting this onto a wall and spray painting, in a sense, only that you do it digitally. So this is also, of course, something you can do to cast a shadow in your scene. And there's a whole lot of conditions you can set to make this test pass or not. And if this test passes or not, you have a range of options you can do when it comes to changing the bits or numbers in the stencil buffer. The depth test is also very important. It's a bit more concrete. It's basically where all the information about depth in your scene is located. So it's basically a buffer that contains the depth of each pixel from the viewer perspective usually. But you can also use this from different perspectives, as we will see later on. But the point is, it stores depth for each pixel. And you can use something called a depth test, which is basically to compare a given fragment C coordinates against the content of the depth buffer. And then you can, for example, say that this test passes whenever this C coordinate is closer to you than anything in behind. And an interesting thing this can be used for, that sort of lies in the cards here, is to do efficient drawing. So you avoid, for example, drawing occluded objects. Because if your fragment C coordinate is behind something in the depth buffer, means that it's occluded and you can remove it from your draw. Or you can say that it is in a shadow, which we will see later. And this buffer value usually has values between 0 and 1. With 0 being the closest point to the viewer and 1 being the most remote point to the viewer. So any questions to this? Alright, so I'll talk a little bit more in depth about the stencil buffer. We will not use this in the shadow map, which is the one I will talk mostly about, but it's very important when it comes to more advanced shadow algorithms, like, for example, shadow volumes, which is probably the next step you will deal with if you go into this in more depth. So I basically already said what this is. Yeah, so the main point is that you allow certain values to be set and some rendering to occur based on these values. And basically, you have one number per pixel or fragment in your rendering, And this can be 1 bit, for example, like it is in this case, where you have, for example, 1s on the white region or 0s in the black regions. Or it could be any number, 8-bit number basically. So you have 2 to the power of 8 values per pixels that you can set in this. And we'll see during these shadow volumes that you actually use this one, a general number, to count in order to tell you whether your object is in shadow or not. But I'll get back to that. Now, this stencil buffer is often used together with the depth buffer, so that if, for example, the depth test fails or the depth passes, you can do things in your stencil buffer depending on whether it passes or fails. And interestingly, you can use the stencil buffer, of course, to cast shadows, but you can also make it in the same reason to cast reflections. Now, I will not talk much about reflections today, I'll just mention that you can do it. So when you made this stencil mask, for example, like here, you could impose some image onto this area that is cut out here, and then you can take this object and flip it back into your scene and blend it with the rest of it, and then it will look like this object is reflecting the environment. So once you learn how to deal with shadows, you can also quite easily deal with reflections as well. But for the rest of the talk, I will focus on shadows. So here's a little bit about the principle. This is just a very simple case. This is one way you can do it. There's a myriad of ways of doing this. But in this particular case, you can say that you have this original rendering, and then you put up this stencil buffer mask. It's very simplified here because of course you have a much more number here inside here than this, but just for illustration. And then when you render this scene again, you will see this this object through this little cutout window here. So it will appear like you're watching it through a window with inside a dark room, for example. And to make this, you could, for example, say that if the stencil test passes, whatever conditions you put into it to pass, then you're going to replace the values in your stencil buffer. So, for example, in this case, you could set them to 1. This is the part of the previous rendering that you would like to keep. And if it fails, you do not override, so you basically have zeros. But the funny thing is you can turn this around as well and say that, well, if the stencil test passes, you don't do anything. And if it fails, you do something. So you're really free to do this in many ways. You can take XOR operations, you can look if something is smaller than or equal to something else. You could put in results from the depth test. So it's really flexible. So this is just one way of doing it. And there's some pages in the Super Bible that explains you all the possibilities you have for dealing with the stencil buffer. So since I don't have time to go through all of this today, I will just mention some of the commands you have at your disposal. So first and foremost, if you want to use your stencil buffer or do the stencil test, of course the buffer is there anyway, then you have to use the GL enable and then input this GL stencil test like you do with any other things you would like to enable in OpenGL. And then you have some available commands that you can use, for example, to make shadows. First of all, you have this GL stencil function separate, which is basically conditions under which the stencil test passes or fails. So in here you will typically put in some polygon, and then you will have some bit mask that you compare against another bit mask, and if something is equal or larger than or equal to or blah blah blah, you will say that the stencil test either passes or fails depending on context. So that's what makes it flexible, but also a bit difficult because there's so many options here. But once this test passes or fails, and again you can say passes or fails, then you can do something. And then whatever you do on your stencil buffer, you could do through this stencil operation function here. And again, you put in some polygon and you put in some bit masks, and you're able to make these stencil masks with this one. Yeah, You have a question?
I have a question about how do we get feedback as to why a test fails?
Basically, that's the output of this function will give you, I think, a 0 or a 1. So I think you put up an if statement, and then whatever you put in here, you will get a 0 or 1 depending on whether it fails or doesn't fail. And then you can go on and use this operation depending on what it returns. Did that answer your question?
Yeah.
Okay, great. So I think that's it. I think it's just a Boolean, basically. It may be more advanced than that, but I think it basically, you just say fail or don't fail. So I think it's a 0 or a 1, most likely. Okay, so if it goes through or fails, depending on what you want to do, you can use this one to manipulate the stencil buffer. Or if you want to do more advanced things, you can set a particular bit mask in this one. Yeah, I'm just finishing this slide. And after that, I'll start with shadow mapping, so we can take a 15 minutes break after that. Okay, so yeah, here is so this one is just more advanced operation than this one, where you can have a predetermined bit mask that you impose whenever you pass or fail this test. Okay, yeah, so we'll take a 15-minute break, so you have time to rest a little bit, and then we'll start off at 13:20.